Okay, so today we are going to look at some exercises about the layer 4, the transport layer. I have uploaded in BIP the text. I hope you can see them. So we can skip the first exercise because it's very simple. Maybe we can get back to it later on. And we can start roughly with the second exercise. So in the second exercise you have a network that is composed of a source, a destination, two intermediate nodes, and all the capacities are given on the three links, as well as the propagation delays. And the condition is that the capacity on link 1 is larger than the capacity on link 2, that is larger than the capacity of link 3. And between A and B, a TCP connection is active and already stable with a stable rate. We can assume that the maximum segment size is 250 bytes. The receive window is smaller, here it should be smaller, than the congestion window and equal to 4 segments. Then we have to calculate the time necessary to transfer a sequence of 144 kilobit, coming from the upper layer, from the transmission of the first segment to the reception of the last segment, of the last acknowledgement. And then we have to assume that we have these conditions given. We have the length of the IP header, the length of TCP header, the length of lower layer headers. They are all given in a symbolic form. There is no transmission error, there is no other traffic, and the acknowledgement length is negligible. So the first question is to calculate the time necessary to transfer that sequence, and the second question is which is the value for the window that would allow continuous transmission on link 1. Okay. Let's see, I make, okay, no, it's impossible to see them, so you can leave it like that, but so we can start briefly drawing the system. Here you have A, the first link, the first router, second router, and then B. These are the capacities and propagation delays. Okay. And so first of all, the length of the file to transfer, let's call it B, is 104 kilobit. Okay. First question is how many segments we have to use to carry this amount of data. If you divide it by 8, you obtain the value in kilobyte, which is 124. It's 13 kilobyte. Okay. How many segments is 13 kilobyte? We have to divide it by the maximum segment size, which was 250 bytes. And this gives you the number of segments in terms of maximum segment size, which is actually 13 by 4. In total, we have to transfer 52 segments, okay? Then, what is the length of each segment in a number of bits? Okay, because that is what we need to calculate the transmission times. We have to add the content of the segment in terms of payload, which is maximum segment size. Then we have the headers of the 3 layers, IP, TCP, and lower layers. So it will be plus HIP plus HTCP plus H lower layer. Okay. These are not given explicitly, so L will remain indicated in a symbolic way. Then what else? We have this indication that the receive window is smaller than the congestion window, okay, and equal to 4 segments. So as you know, the transmission window is always equal to the minimum between the congestion window and the send window, the receive window, sorry. Actually, transmission window is usually called send window. Okay. So now we know that the receive window is the smallest one of the two. So basically, in this case, only in this exercise, send window which will be equal to the receive window. What is the receive window? Is that value that is inserted in the acknowledgements that are sent by the receiver to the transmitter, and it basically implements the flow control. Okay. So the connection, TCP connection in this particular case, is controlled according to the flow control. So now we have to answer the numeric question, which is what is the time that it will be taken to transmit this file of size B. Okay. And we have to always, for these exercises, we have to always to draw a picture that is our usual time diagram to show the exchange of these packets. So here we have the A, B, and then the two intermediate routers. These are the places where we have to look at the packets. Okay. This is A, R1, R2, and B. Now, we have to assume that at a certain point we start transmitting the file, and here the text says that the connection when the file is transmitted is already set up and stable. So in this exercise we don't have to consider the setup phase. The connection is already working. And then we can start drawing the sequence of packets. So since we are transmitting with a send window which is equal to the receive window and is also equal to 4 times maximum segment size. This is what is written here in the text. Okay, it means that I can transmit only 4 segments in a window, maximum 4 segments in a window. Now the question is that before we can do the drawing, we have to ask if the transmission will occur without stops, or if the transmitter will have to stop after the exhaust of the window. This, as usual, depends on the round trip time in relation with the length of the packet, and so how many packets can be inside the window. So let's say that we have this situation that so we don't know a priori what is the size of the value of the round trip time, because here we have this value L, which is given in a literal form. So we have to do 2 hypotheses, okay, one hypothesis and the other. So the first hypothesis is that the size of the window, I call it W just to be short, okay, multiplied by the number, the total transmission time, let's call it T, of a segment, is larger than, let's say, also equal to the round trip time. Okay. So you know that in this case, when the first packet is sent, the acknowledgement on the first packet will arrive after 4 packets, so a full transmission window are sent. Okay. So in this case, we can start drawing this kind of picture. So we have the transmission of the first packet. It will contain the payload, which is MSS, plus all the headers. Okay. Then we send the second packet. The third, packet number 4. And then we have to stop because we have run out of the transmission window. What happens to these packets? We have a propagation time. After a propagation time, they arrive to router number 1. Okay, we know that the capacity of the output interface of router number 1 is higher than the capacity of A, of the output interface of A. So it means that the transmission times out of R1 will be smaller than the transmission times that we had before. Say that we have this situation. Then we have another propagation phase. Let's say that we have another propagation delay. Actually, all the propagation delays are the same. propagation delays. No, they are not given. Okay, so we don't know that. So let's say that we have this situation. Then we know that the capacity of the second, the interface of the second router is even smaller. Okay. And finally, we will have the last propagation delay. This is what happens, and it is important to know that the capacities of R1 out of R1 and out of R2 are smaller than the capacity of are higher than the capacity of the first transmitter, because in this case we will not have any queuing at the intermediate interfaces. Otherwise, if it's not like that, you have to consider also the queuing delay. Then the text says that the ACK length is negligible, so when ACK are transmitted, they go directly. Now this is not precise, but okay. They arrive to A, the transmitter. This interval that you have from sending the first packet to the reception of the last of the first ACK is the round trip time. Okay, this is round trip time. So how many? How can we describe the transmission of the file? Let me just make some more space. So we will have groups of 4 segments that are transmitted one after the other, because after this round trip time we will have the same as before, and until we have transmitted all the bytes of the file. Note that in this case the file contains an exact number of maximum segment size, which means that all the segments will have the same size, which is the maximum possible. Okay. If the number of bytes of the file is not an integer multiple of maximum segment size, then you will have n-1 segments that will be maximum segment size, and then the final segment that will be shorter. Okay. But this is not the case, so they are all equal. And we have 52 segments to send. Each time we send 4 segments. Until we are able to send 4 segments, the history repeats without any change. So we can say that the total time of transfer time, let's call it TB, will be equal to the number of groups of 4 segments that we can make minus 1. Okay, so we can write it as 52 divided by 4 minus 1, and this multiplies the round trip time. Okay. You have to imagine that this situation that I have depicted here repeats it the same. How many times? Actually, it will be repeated 52 divided by 4 times, but we have to be careful, because in the last transmission time we must take into account also the arrival of the segments, okay, of the arcs. So after this quantity here, then we have to look at what happens in the last repetition of this segment. So imagine that this is the last window that is transmitted. Okay, we have to wait to for the arrival of the last acknowledgement. So let me see if I can copy this thing here. Yes. Okay. I moved everything. No. Unfortunately, the picture now is a little bit strange, but in any case, this is the time when the last ACK arrives to the destination, to the source, to A. And if this is the last repetition, last window that was transmitted, what we have to put here to complete the transmission time, the transfer time, we have to consider the time the last ACK is arriving. So as usual, we can go down this way. Then here we have can go up, and then we have we arrive to that point. This is a round trip time again. This in yellow, and then finally we have also to add this part here, this segment, which is 3 times the transmission time of a single segment. Okay. So all the segments are transmitted in groups of 4, and so you have this quantity here that accounts for the transmission of all the groups of 4. Each time you transmit a group of 4 segments, you have to take into account that you have the transmission of a round trip time. Okay, the time that is taken is the round trip time. Then the transmitter stops, and then it transmits again other 4 segments. The last repetition of this phenomenon, it takes more, because you have to take into account that we must wait for the last segment. Okay, so this is the calculation of the last part of the transmission time. Okay. What is t, the value of t? Okay. The only transmission time that is relevant in this exercise is the transmission time of A, okay? Because that is the one that determines the duration of the window. Okay? So T will be equal to, the name is L, divided by C1. Okay? L is the total length of the segment, taking also all the headers into account, and this is the time that we must use. Okay. Instead, what is the value of the round trip time? The round trip time is the yellow line that you see there. So in order to calculate it, you have to sum L divided by C1 plus L divided by C2 plus L divided by C3 plus 2 times tau 1 plus tau 2 plus tau 3. Okay. This is the usual calculation. If you see the yellow line, you find all the segments that are the components of this. Is it clear? Now we should look at the other case when we have that this is case 1, let's say, call it A. Now we have that the round trip time is less than W by T. Okay. So what happens in this case? I make a fast picture, not very precise, but be fast. We have this case here. This will be the round trip time. Now we know that the window is 4 times T1. So this is what happens. The first arc, the arc on the first segment arrives before the window is transmitted completely, and therefore the transmitter will go on sending packets, okay, until we arrive to the last segment. So also in this case, we have to consider all the segments except the last one to calculate the total transfer time. And we know that this file generates 52 segments. So we can say that the total transfer time is equal to 52 by 52 minus 1 by T, which is this component. And then we have the last component, what is that value? What is that we have to add? Yes. Okay. Oops. Okay. So we have 51 transmission times plus round trip time. Okay, I leave you the last question that is this one to you. You can do it by yourself, it's quite easy. So now let's move to another exercise. Questions so far? Let me skip exercise number 3 and go to exercise number 4. So here we have at time 0 a TCP connection between host A and host B is activated. We have to compute the time when the transmission on link 1 becomes continuous. Okay, this is the first question. Second question, how much time does it take to transfer a file of 2 kilobytes from the connection setup to the reception of the last ACK? The data of this connection are the following. Header lengths are negligible, so the packets that are transmitted on the interfaces are equal to the size of the segment, of the payload of the segment. Receive window is 4000 bytes, slow start threshold 400 bytes, maximum segment size 200 bytes, the ACK size is 20 bytes, okay, which is equal to the setup control packet size, which is also equal to the setup control packet size. Finally, the connection is opened by A. This is quite a classical exercise, and we have to solve it, obviously take into account also of the congestion control, because as you can see, here we have a slow start threshold specified, which is a variable that is for the congestion control. Receive window is 4000 bytes, which is equal to 20 maximum segment size. Okay, so we can guess already from now that at least at the initial phase of the connection, the connection will be controlled by the congestion control. So, first of all, we can do some calculations. Here we have, another thing is that you see that also in this case, the capacities of the interfaces are increasing hop by hop, and in particular, the first one, the third one is the double of the second, which is the double of the first. So also in this case, we will not have queuing at intermediate nodes. Here is not explicitly said, but we can assume that there is no other traffic than the segments of this specific connection. And moreover, in this case, we have constant propagation time in all the links. So we can start computing the transmission times. So since basically the transmission time in general is given by L divided by C1, and since we don't have the headers, we don't have to consider the headers, at least for the first segment, the length will be equal to the maximum segment size, and at most the last segment can be different. Okay, we have to check it afterwards.
To unlock the phone first. Which one?
Okay, so the length is 200 bytes, so we have 200 by 8 divided by 25 kilobit per second divided by 25, the result is in milliseconds. Okay. 200 divided by 25 is 8, so we have 8 by 8, which is 64 milliseconds. Then we know that T2 will be the half, because the capacity is double, and T3 will be again the half. Okay. So we can also calculate the round trip time. Round trip time, I don't draw the picture immediately, but you know it. It will be given by T1 plus T2 plus T3 plus 2 times tau 1 plus tau 2 plus tau 3. Okay. Sorry, we have also to include here the transmission time of the ACKs, because in this exercise the ACKs are not negligible in length. Okay, they are 20 bytes, so it will be also plus TACK 1 plus TACK 2 plus TACK 3. Tau I is equal to 15 milliseconds. TACK 1, we have 20 bytes, so it's 20 by 8 divided by 25 milliseconds, which is very bad. How much is it? 6 point. Okay. And then you also know TACK 2 and TACK 3. I have already the final result, it should be correct. So the round trip time finally should be 213.2 milliseconds. Okay. So now we can look at the picture. The usual time diagram. More or less. So we will have the opening phase, and here the text says that the transmission time of the packets, the length of the control packets that are opening the connection is equal to the length of the acknowledgement packets. Okay, this is the opening phase. Okay. Then, as you know, we have the freehand shaking procedure. So the first packet is only for signaling, the second also. After the confirmation, the sender can start sending the last packet of the freehand shaking, but in the last packet it can start sending also data. So we will have, at this point, we will have the transmission of the first segment of the connection. Let me make it 4. Okay. And then we have the transmission of the AX on the other side. Okay. Why? So this is also enables us to define the round trip time, so graphically. This is a round trip time, okay? Why I wrote a single packet, a single segment in the first round trip time? Here we are at the beginning of the session. Okay. So how is the transmission window? forgot to write this. So the receive window is equal to 4000 bytes. So is equal, since the maximum segment size is 200 bytes, the receive window is 20 times. Okay. So how, at the beginning of the connection, what kind of send windows we have? As we have seen in the previous exercise, send window is always set to what? Send window is the window that transmitted. What is a send window? It's set to the minimum send window is the minimum between, okay, it's the minimum between congestion window and receive window. So what is in this case congestion window? At the beginning of the session, the congestion window is one. So the congestion window at time t equal to 0, let's say, which is time t0, is equal to 1. The receive window is equal to 1 what? 1 MSS. Okay, it's always normalized in terms of the number of MSS. Receive window is 20 MSS, so clearly the congestion window is the smallest. So send window at the beginning at time t equal to t0 will be 1 MSS. This is why I can send just one segment. Okay. Now we have to follow the evolution of the congestion window and send window in order to understand how this connection will continue. So in the next round trip time, we have sent one segment, we receive one ACK. What happens to the congestion window? Becomes 2, okay? Because we are, well, first we have to check, okay? Are we in the slow start phase or not? Okay, so in order to understand this, we have to look at the slow start threshold. Okay, and in this problem, the slow start threshold is set to 400 bytes. Okay, so this means that the slow start threshold is equal to 400 divided by 200 to maximum segment size. So at the end of the first round trip time, we are still in the slow start condition, in slow start phase. So what happens in the next see if I can copy this. Okay. What happens in the next phase? That we will transmit 2 packets instead of 1. Okay. Now, after a round trip time, so we are in this and here, we receive an ACK, okay? But if you apply the congestion, the slow start threshold, this means that you will increase the window to 3, okay? In this case, we have overcome the slow start threshold. So from this moment on, we are actually in the congestion avoidance phase. Okay. So this is a congestion avoidance. So far it has been a slow start. So in the congestion avoidance phase, we have to increase the size of the window by just 1, let's say 1 divided by W. This is the unit, but in this case, in the last, the previous window contained 2 segments. Okay. So we can send another segment here, and then at this time also the ACK of the second segment was received. So it means that the congestion window will increase by 2 multiplied by 1 over 2. So it means that it will increase by 1. Okay. Unfortunately, I run out of space. So let's see if I can copy all this part here. So here we will have the transmission of 3 packets, okay, 3 segments, and then then what happens in the next round trip time, that we will transmit 4 segments, because we are still in congestion avoidance. Now I don't draw everything, and so on. So now we have to check when the transmission becomes continuous, because when the transmission becomes continuous, then the transmitter will not stop at each round trip time waiting for the next round trip time. Okay? And again, we can say that in this exercise, as in the previous one, the bottleneck is for sure this link, because it's the slowest link in the network. And so we always have to check the round trip time against T1, which is the transmission of the segments on the interface, out of the interface of A. Okay. So we have to look at this relation. W by T1 should be larger than the round trip time. Okay, this means that W should be larger than round trip time divided by T1. And if you do this ratio, we know T1, we know round trip time. T1 is 64 milliseconds, and round trip time is this 213.2. And this comes out to be 3.3. Okay. So it's a little bit larger than 3, so it means that despite the drawing which is not exactly in scale, already starting from this instant to the next to all the next, transmission will be continuous. Okay, because already in the third round trip time we have that the transmitter is able to send all the window before the return of the return of the up on the first packet. So here transmission will become continuous. Okay. We have also to compute this time here, which is the setup. Let's call it RTT prime, which is the setup time. So this is the time that we are looking for in the text. TC is the time by which the transmission becomes continuous. So we can see that we can put in together the two pictures. I cannot do it physically, but you can imagine it. TC is equal to the round trip time prime, which is the setup time, plus then we have 1 and 2 round trip times. Sorry, 3 round trip times. 1, 2, and 3 round trip times. Okay. Which turns out to be 752 milliseconds. Okay. So the second part is the second question is the time that is necessary to transfer a file. Point 2. So the file has a length of 2 kilobytes. Okay, 2 kilobytes means that it is equal to 10 maximum segment size, exactly 10 maximum segment size. So all the segments will be equal, have a length of a maximum segment size. And we have to send a total of 10 maximum segment size. So if you look at the picture here, let's say that you are transmitting the file, you send 1, 2, 3, 4, 5, 6 segments in the discontinuous transmission mode. Okay. The rest of the segments are transmitted in a continuous transmission mode. So if you want, we can do a fast picture. So here we have the opening phase. Then we are sending first one, and then from this point on the transmission is continuous. This is RTT prime, then this is RTT, here we have another RTT, okay, and we are in this time here. This is TC. And we send 1, 2, 3, 4, 5, 6 segments. Then we have to send other just 4 segments, because then we send 10. So 1, 2, 3, 4. This is the final segment. And we must calculate the transfer time until the last acknowledgement is received. Okay, so here you have to assume that we have a final round trip time. Okay, so in the end, the total transfer time of the file is equal to opening of the connection. Then we have 3 times RTT. Then we have this intermediate segment, which is equal to the transmission of 3 segments on the first link. So it will be 3 plus T1. And finally, we have this final segment, which is another round trip time. Okay. Questions? So in the remaining time, I would like you to try to make an exercise, which is actually very similar to this one, but it's much simpler because you have only 2 points, and this is exercise number 3. So this is from a TCP. So a TCP connection is used to transfer a file of 39.5 kilobyte using the following parameters, and then there is maximum segment size, round trip time, assumed to be, of course, constant, which is just for the exercise, initial timeout, which is set to 2 times the round trip time. And then the other initial conditions are the receive window size, slow start threshold, congestion window size. Then we assume that there is an error at time 3 seconds, and all the segments are lost due to this error, or the segments that were in flight, in transmission from the source to the destination. At time 4.5 seconds, the receiver indicates the receive window equal to 2 kilobytes. And so in these exercises, most of the time receive window is belongs to the inputs and its data. Draw the evolution over time of congestion window, slow start threshold, and receive window. Calculate the time to transfer the file. So you can notice that in this kind of problems, there is no indication about the capacity of the leads, the transmission leads. Okay, so that is not known. So we have to assume a model that is independent of the transmission time, basically. And in this case, you can assume that all the segments, when they are transmitted in a certain transmission window, send window, they are transmitted at the same time, so in just one instance with a negligible duration, and they are then received, and later on the acknowledgements of these segments that were received all in the same time are received also in the same time, and after precisely 1 round trip time. Okay, so the round trip time is given. It takes into account every delay, so including possible transmission delays, but you don't know what is exactly the composition of this round trip time because you don't have any view on the underlying network. Okay, so in this case we have to assume this type specific model, and when we are dealing with this model, we can use a graph, which is that you will see, it's quite common. It's a graph in which you have on the x-axis at the time, which is slotted in round trip times, and on the y-axis you have an indication of size, and also in this case you slot it in terms of maximum segment size. You can also assume that all the segments, except maybe the last one, are of the maximum segment size. So this is the graph and that we are going to draw. And then on this graph you can plot the behavior of these three variables: congestion window, slow start threshold, and receive window. Okay, since you have a y-axis which is in terms of maximum segment sizes, you can normalize each of these quantities in maximum segment size. So the first step in this kind of problems is to normalize everything in maximum multiples of maximum segment size in the case of the size, and multiples of round trip times in the case of the times. So you have basically here that the number of segments that is that you have to transmit, which is given by the size of the file, okay, will be equal to 39.5 kilobytes divided by B divided by maximum segment size, 39 kilobytes divided by 500 bytes, okay, which is maximum segment size. And this results in 79. So the number of segments that we have to transmit is 79. And each segment is equal to the maximum segment size. Then we have that the receive window at time t equal to 0, so the initial receive window, is 12 kilobytes divided by 500 byte, and this is 24 maximum segment size. Okay. Slow start threshold also at time t equal to 0 will be 8 kilobytes divided by 500, and that is 16 maximum segment size. And finally, the congestion window is we have to initialize it. So since we are assuming that we are starting our session, our TCP session at time t equal to 0, how much would it be, the congestion window at time t equal to 0? How much is the congestion window at the beginning of the connection? I understand that this is the last chapter, so the previous chapter, so you can we are talking about layer 3, but I hope that at least the congestion window at the beginning of the connection is 1. Okay, we are at the beginning of the connection, so it's initialized to 1 maximum segment size. Obviously, in all these exercises, we assume the TAHOE flavor, which is the basic behavior of the basic version of TCP. Then we can also convert the times, so the time t1, let's say, that is equal to 3 seconds, that is when the error is occurring, so all the segments are lost. Since we have that the round trip time is 500 milliseconds, will be equal to 6 round trip times. Okay. And then we have also that time 2, which is the time at which we have a change in the receive window, is 4.5 seconds, which is equal to 7, yes, 6 plus 2, 8, no, 9 round trip times. Okay. And also we can say that the receive window at time t equal to t sub 2 is going to 2 kilobyte, so it will be equal to 2 kilobyte divided by 500 is 4 round trip times. Sorry, 4 maximum segment size. Okay. So now that we have all these normalized data, we can start drawing the graph. No. So here we have the time, here we have the size in terms of maximum segment size, the time in terms of round trip times, and we have to go until 8 secondi, 8, 16. And on the other side, we have to go up to well, this is even too small. Okay, so on the other side we have to go up to 30. Okay. So first of all, we can draw the behavior of the receive window, since this is something that is given, and so it's quite simple. We can draw it, let's say, in red. Initially, the receive window is set at 24 maximum segment size, and then at time t equal to 2 it goes to 4 maximum segment size. Time equal t2 is this one, at 9 round trip times. So we can draw a first line. 24 is roughly here up to this point, and then it goes to 4. Okay. Then we can also draw the slow start threshold. Let's use the green. The slow start threshold initially is set to 16 maximum segment size. Now you know that the slow start threshold remains the same until we have an event occurring that changes that resets the congestion window parameters, and this event is the loss of segments. And we know that the event is at time t1, which is, sorry, 6, at 6, t1 is here, okay, at 6 round trip times. Actually, when the loss occurs, which is at t1, then we have to wait, because the transmitter recognized that there was a congestion event only after a timeout. So only after one timeout has lapsed. So before from the event of packet of segment loss until the time when all the parameters of the TCP connection are reset, we have to wait one timeout. And we know from data that the timeout is initially set to 2 times the round trip time. Okay. So here in the graph, this is the timeout, and nothing moves in the transmitter until the timeout has expired. Once the timeout has expired, then the slow start threshold will be reset, and we start again the slow start process, starting from the transmission window equal to 1, because congestion window will be equal to 1. What is the value of the slow start threshold that we have to use in the second from 8 round trip times on? We still don't know. We have to wait and to understand what happens with the congestion window. So let's use the black to draw the congestion window in this graph. Since everything is slotted and all the segments are transmitted at the same time, our curve that is representing the congestion window will be dotted, will be a discrete set of points. So we have to build one by one. So initially we are here, and the congestion window is set to 1. Okay. When the congestion window is set to 1, the first segment is sent. And we are clearly below the slow start threshold, so the first phase will be slow start. Okay. So after one round trip time, all the acts that been of the segment that was sent are received. Here we don't have any error, so they will be received all. And what happens to the congestion window? We are in the slow start threshold, so each time we receive an ACK, the congestion window is increased by 1. Okay. 1, of course, always in terms of maximum segment size, so it's always normalized. So it will go to 2. Okay. Then 2 segments are sent at the same time. No errors occur, so after one round trip time, we receive 2 ACKs. And since we received 2 ACK, we are in a slow start threshold, congestion window goes to 4. Okay. When you are drawing this graph, you usually have to draw a dot, and then near to the dot you write how many packets are sent and what is the size of the congestion window. Then we have, so the congestion window here is in black. Then we have another round trip time. All the acts are coming back, so we go to 8. Okay. Another round trip time, and all the acts come back, we arrive to 16. When we are at 16, we are hitting the slow start threshold. So now we are entering the congestion avoidance mode. Okay. Here we are lucky because we are entering the congestion avoidance mode exactly at the beginning of a new, let's say, group of packets that are sent. Sometimes it can happen that you don't have this situation, but the congestion window can be, let's say, the number of acts that you receive are larger than the slow start threshold. So in that case, you have to be more careful. But we are not going to use that specific cases in this course because it's only 5 credits. It would require too much time. Okay. So you will find only these special conditions. Then now we are in the congestion avoidance mode. We send 16 packets, 16 segments. We receive 16 acts, and this means that we increase the congestion window by 1, because in congestion avoidance mode, for each ACK received, the congestion window is increased by 1 divided by the value of the congestion window we have. Okay. So it's 1 over 16 by 16, which is 1. So in the next round trip time, we are at 17. Then again, we receive another, it's another round trip time, so we are, actually 17 should be a bit lower. Here we arrive at 18, okay? Now we have the outage of the network. So all these 18 segments that are in flight gets lost. And so we have to wait for a timeout, and at the time t equal to 8 round trip times, we have the reset of the TCP connection. And what happens? The congestion, the slow start threshold is set to a value which is equal to flight size divided by 2. Okay? In case flight size divided by 2 is larger than 2, otherwise it gets 2. In this case, flight size is exactly given by the number of packets that were sent and were not received because they all got lost. So it's AT. It means that the slow start threshold will be set from this moment on to A9. Okay. Here it was 16. Sorry, 16 is, okay, 16, and then it's 9. What happens to the congestion window? Congestion window is reset to 1. So here, at this time, we send another segment. Then we are again in the slow start in the slow start mode. So the next time it will be 2 segments. Now we must be careful because we have also to start counting how many bytes of the file has been transmitted. Okay, we know that the byte is the file was 79 segment long, and so we have to count how many segments have been transmitted so far. Let's use let's say the orange color. Okay, so here we have transmitted 1, here 3, 7, 7 plus 8 is 15. 15 plus 16, 31, plus 17 is 48. Tell me if I am wrong. Plus 18 is 66. Okay. Then here, be careful because when we are here at the time t equal to 8, this is not a new segment. We are retransmitting the segments that were lost, okay? Because in TCP, you know that we have the retransmission. So we don't have to go on with counting the segments that have been already transmitted. So here we have 1, 2, and then next time slot we should be at 4, okay, and in fact we go to 4. The next time slot we are still in slow start, so the congestion window gets to 8. The congestion window arrives here, okay, but we cannot transmit 8 segments because now we are constrained by the send window, okay. So the transmission, the receive window. Send window, it's always set to the minimum between the congestion window and the receive window. So we are constrained to send 4 packets, 4 segments. And here we have transmitted 4, 8, 10, 11. We go on again, is 4, and we got to 15. So we have transmitted 16 plus 3, 8, 19. Okay, now we can go on with counting the segments, okay, because we have retransmitted all the 18s that were lost, and we have also transmitted one more of the segments of the file, okay. 4, the file was 79. So let's count. So 67, sorry, plus 4 is 71, plus 4 is 75, plus 4 is 79. Okay. So now we have finished transmitting the file. So the total transfer time that was required by the exercise for this file is 16 round trip times, which is equal to 8 seconds. Okay. Questions? So in the 10 credit course, with this kind of exercises, usually we, for instance, define 2 outages of the network into different times, or multiple outages. But for this course, they will be always quite simple, like this one. Okay, this is quite short, and with just one loss, which is you take note, but however I will then put everything in BIP, and also there are the video recordings that I will put on YouTube.